Let's ask another question. Suppose we had a population that was growing exponentially. And it's growing exponentially at the rate R, Here's a question. How long will it take for that population to double in size? So we want to know how long it takes to double. What was our exponential model? It was that kt equals k0 e to the rt. We're given an r, it's growing at the rate r, and we want to know with this rate, we want to solve for t that gives us the time that it takes to double. Well, to double, we want kt equal twice k0. So let's rewrite that as 2 times k0 equals k0 e to the rt. There's a k0 on both sides of that. There's a k0 here and a k0 here. We can cross those two out. And what we end up with is that to double in size, we get 2 equals e to the rt, and now we have to solve for that t. How do we do that? We're going to take the logarithm base e, so that's just the log of 2 equals rt, and that means that our t doubling time, t double, equals, how do we do that? It's going to be the log 2 divided by our growth rate, r. That's odd. The logarithm of 2 is a constant. What is the logarithm of 2? Well, I'm sure you all know this. It turns out that the logarithm base e of 2 equals 0.6931 something. So, the doubling time, t double, if the population is growing exponentially with the growth rate r, that is going to be 0.6931 over the growth rate r. If r were 0.01, 1% per year, then t double would be 0.6931 over 0.01 equals 69.3 years. If r were 0.02, then t double, the doubling time, is 0.6931 over 0.02, and that is going to be something like 34.66 years. This turns out to be a rule that has been known for a long time. This rule has actually been known for longer than the logarithms have been around. Our exact rule is that t double, the doubling time, is going to be the logarithm of 2 divided by the growth rate. We have an approximation and that is, let's see, if that's 0.6931, my approximation is that that's roughly equal to 70 divided by R in percent. So if it were 0.01, that's 1%. So we take the number 70 and we divide it by 1%. So that's 1. That's R in percent. So we'll take roughly 70 years. We know exactly it's going to take 69.3 years, but our approximation is that it's 70. It turns out that this approximation is an approximation, a close version of this approximation is taught in business schools. It's called the Rule of 72. And we'll say a business school rule of 72, and that rule says you take 72 and you divide it by the interest rate in percent, and that will tell you how long it takes to double your money. So if you can invest your money in an account that returns you an investment that promises you 4% per year, then it will take you 72 divided by 4. That is going to be 18 years to double your money. We actually happen to know that it is at 4%. It's actually 0.6931 divided by 0.04. But in business schools, they just teach you these approximate rules, and that our approximate rule is the rule of 72. In case you want to know, the reason why is because the number 72 has lots of even factors. 72 is evenly divisible by 1, by 2, by 3, by 4. It's almost evenly divisible by 5. It is evenly divisible by 6. It's almost evenly divisible by 7. It is evenly divisible by 8 and 9, and almost by 10. So in business schools, this rule of 72 gets you close. It's the kind of calculation you can do very quickly. We don't have to do it quickly like that. We can remember it's 0.6931, the logarithm of 2. So that is our simple rule. The exact rule is this logarithm of 2 divided by the growth rate R. What happens if R is negative? The population is not growing. What if the population is shrinking? Then our question is, how long does it take for the population not to double in size, but to halve in size, to be half as large? In that case, kt equals k0 e to the rt, and now we want kt equals half of k0. So we're saying 1/2 k0 equals k0 e to the rt. As before, we see that these k0s cancel out, and we end up with 1/2 equals e to the rt. So we can get the logarithm of 1/2 equals rt, and so this t half equals the logarithm of 1/2 divided by r. What's the logarithm of 1/2? Well, it turns out that it's 1 over, I just said that the log of a ratio is the difference in the logs of the numerator and the log of the denominator. So that is going to be the log of 1 minus the log of 2 divided by r. What is the log of 1? It's 0. So this thing is going to be minus the log of 2 divided by r. And what is the log of 2? We already saw it up above. It's 0.6931. So this is going to be minus 0.6931 divided by r. We said r is less than 0. R is negative. So it turns out that the t double and t half both look like 0.6931 divided by r. If r is negative, that's going to be a minus 0.6931 divided by r, minus by an r which is negative. In both cases, it's going to be the number of years. That's going to be positive. Number of years until that population is cut by half. So it's the same formula. In both cases, it's going to be this log 2 divided by r. You've learned twice as much. You have an equation, a formula that works both when r is positive and r is negative. It will just tell you how many years until the population either doubles if the growth rate r is positive or shrinks by half if r, the growth rate, is negative.